So recall that a domain is called a Euclidean domain if basically the division algorithm works in there. So you have a function from the non-zero elements of R to non-negative integers called nu, such that if you give me any two elements A and B in R with B non-zero, then you can find Q and R in the ring such that A is BQ plus R, and so Q is the quotient and R is the remainder, and nu of R is strictly less than nu of B, or R is 0. So the nu is sort of a measure of the size of an element, and when you're given any two elements, you can always divide as long as what you're dividing by is non-zero, so that you get a quotient and a remainder, and the remainder is either 0 or the remainder has strictly smaller size. So we saw Z is an example, polynomial ring in one variable over a field is an example, and then let's prove that this is also an example, Z adjoin I, which means all numbers of the form a plus bi where a and b are integers. So this is a Euclidean domain with so this is a Euclidean domain with the Euclidean valuation nu being the absolute value square. So nu of a plus ib is a square plus b square. So let's see how the division algorithm works in this ring. So you give me two complex numbers. Somehow I'm using, I'll stay consistent with my notes, so I'll use, instead of a and b here, I'll use z and w. Let z equals a plus bi and w equals c plus di be two elements of zi. So a, b, c, d are integers and w is non-zero. Then you see w and I times w, which is w 90 degree rotated in the complex plane. So here is a picture of the complex plane. These are two linearly independent vectors. So it's just two-dimensional linear algebra, linearly independent vectors in the complex plane in C. So if you give me any vector whatsoever, for example z, I can write it as a real linear combination of these two vectors, because these two vectors form a basis for this plane. So we can write z as some real number times w plus some other real number times iw for some alpha, beta in R. In fact, alpha and beta would lie in rational numbers, but we'll see in a bit. But this is good enough. Now if you give me any real number, I can always find an integer which is within half distance from it, because if this is the real line and these are the integer points 0, 1, 2, minus 1, etc. You give me any real number whatsoever, I can always find an integer which is within half a distance of it, either on the right or on the left. So there exists, let's choose those integers. Let's call them m1 and n1, such that alpha minus m1 and beta minus n1 have absolute value less than half. We'll call them u1 and v1. have absolute value less than or equal to half. Okay, so if you give me a alpha that is here, then I'll choose 2. If you give me a alpha that is here, then I'll choose -1, etc. So now your z is alpha w plus beta times iw, right? Up here. So that is same as alpha you see is u1 plus m1. So sort of m1 is the integer part and u1 is the fractional part of this alpha. And similarly beta is n1 plus v1. Again, n1 is the integer part and v1 is the fractional part. So this is same as m1 w plus n1 iw. So that is m1 plus I n1 times w. That is a element of the ring zi times w plus what's left. What's left is u1 plus I v1 times w. So I let this be the q and this be the r. Okay, so now let q be m1 plus I n1. That's the element of zi, and r is the rest. So now I have written z equal to qw plus r. And since z, q, w are all in zi, so is r. Note r is equal to, because to begin with these were some, who knows, we chose real numbers, right? R is z minus qw, and this is in zi again, because z is in zi, w is in zi, q is in zi, and zi is a ring. And finally, let's calculate the size. The size of this is the size of u1 plus iv1 times the size of w. But that's same as both the real part and the imaginary part of this number is less than half. So this is less than or equal to actually u1 square. So let's take the square. The size of this number is u1 square plus v1 square times w square. But both u1 and v1 are less than half in absolute value, so this is at most a quarter, this is at most a quarter. So this is less than or equal to half absolute w square, which is strictly less than w square. So absolute r is less than absolute w. That's what you wanted. Or actually, we are using the absolute value square, so this is already good enough. Yeah, so let me just illustrate this quickly by doing a division with remainder. So I am going to take, I drew it out already, let's take w equal to this number, 3 plus 2i. And then I'm going to take z equal to minus 8 plus 5i. So that's 1, 2, 3. So this is 0, and then zi is this integer grid, right? This black, all these black dots make zi. And so it's minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, minus 7, minus 8. Plus 1, 2, 3, 4, 5. That's our z, let's say. And I want to divide this z by this w. Okay, so then what you do is you look at the all multiples of w. Now these green dots are all multiples of w. So here's w, here is 2w, here is 3w, but then here is iw. You see, when you multiply by I, you go here. I is in the ring. Here is w plus iw, meaning 1 plus iw. Here is negative 1 plus iw, etc., etc. So these green dots is the ideal generated by w. All these green dots. Yeah, that's the picture of the ideal generated by w. So let's write that. Set of green grid points. So these are all AW, where A is in the ring. So what you need to do is you need to find one of those green dots which is very close to Z, so that the difference is it's smaller in magnitude than W. So for example, what you're going to choose is, in this case, I think you take minus W is here, and then 2W is here. So let's take this one, that's the closest. So that is going to be minus W plus 2IW, you see. Oops. That's minus W, that's 2IW, because this is IW. So this is minus 1 plus 2IW. So this is going to be my quotient, and then this much is my remainder. And if you want to do that calculation, oops, we make some space here. What you do is you calculate Z over W. So that is minus 8 plus 5I divided by 3 plus 2I. And if you multiply by the complex conjugate, you get minus 8 plus 5I, 3 minus 2I, divided by 3 plus 2I times 3 minus 2I. And that's, the denominator is 3 square plus 2 square, which is 13. And the numerator, if you calculate, you'll get minus 14 plus 31I. And now you can write that as minus 14 over 13 plus 31 over 13I. Yeah, so those were the real linear combination. And now you take out the real part, and then now break that into the integer part and the fractional part. Yeah, and here is this now. So that's minus 1 plus 2I plus 1 over 13 plus 5 over 13I. So now I have written Z as minus 1 plus 2I times W plus another guy, R, where this R is in magnitude smaller than, so this is the remainder. Yeah, which is this number times W. And R is W times 1 over 13 plus 5 over 13I. Or rather minus 1 over 13, I'm sorry. Minus 14 over 13 is minus 1 minus 1 over 13, which turns out to be minus 1 plus I. Okay. And you can check that that has magnitude less than W, because that's how we chose it. And you see that indeed R is minus 1 plus I. Okay. So that's how division with remainder works.